A very good morning, everyone. Thanks for coming, and I'm glad you all made it. After the last night event, it was an amazing event we had with the reception. This session is on network engineering workshop, and the focus of this session will be updates from North America and Asia. In total, we have 4 presentations. We will have presentation from Internet 2, ESNet 6, from Hans, from Transpec, as well as Akashi-san on SciNet 6. So let's start off with from Chris from Internet 2, who is coming in remotely. Chris, can you hear us? Yeah.
I can. Good morning.
Good morning, Chris. Oh, is it morning or evening?
It's very much evening here, although it'll be morning here shortly.
Okay. The floor is yours to share the screen and make the presentation.
Thank you very much. I'm sorry to not be there with you all, but happy to be able to come in remotely. My name is Chris Wilkinson. I'm the Director of Planning and Architecture for Internet 2. Internet 2 is the, or at least one of the domestic networks that provide services in the United States. And I'm here this morning to talk about our sort of community-driven approaches for supporting both international engagement and data-intensive science in the US and beyond. So I always like to start with a good baseline. These are sort of the common themes that we hear over and over from the GNAG and the larger community, that we all want our worldwide networks to be able to coordinate and function as a system, to provide best-in-class resources that can couple not just network, but also edge computing and storage. For Internet 2, at least, that we're providing programmatic support and infrastructure for grant-funded programs, data-intensive science, international transit, and also integrating security and integrity of those services for those uses. That's all being driven through software, automation, and APIs. That allow for the integration of those network resources into the larger global and domestic fabrics, that conserves network resources and provides backup capabilities. And that we're also supporting things that like caches, regional data lakes, HPC computing, and other uses through intelligent overlays and control planes, and that we're supporting experimental purposes as well. Like P4 experimentation, SRv6, which is very much not experimental, but key, and 5G, along with platforms like NRP and Sense. So these are all the types of things that we have to think about as we, as Internet 2, figure out what is next for the platform and for our larger collaborations and consortiums. So I'm going to start with some domestic things that we're doing that all build towards our international support. And then I'll talk a bit about some new initiatives we have on our international programs. So these are the types of things we're thinking about at Internet 2, very much software, automation, how we're interfacing with our platform and our services. At Internet 2, we're developing Insight Console, which is our new front end, which will eventually replace OESS, which many of you are familiar with. We're developing new APIs that underlay that new console platform, along with the orchestration platform that sits yet below those, NSO and MCP. So software, automation, and provisioning are all very much key in what we're doing. Of course, our international and research program support is key. We're pushing through with 400 gigabits per second, both on our core platform and our international platform. We're building DTN support into the core through the OSG, Open Science Grid, consortiums. Those are both campus-based in the United States and on the core, filling in the gaps. And then we're working to support all of that through our core integration. So it's not just, they're not just add-ons, they're actually integral to the core itself. And I'll talk a little bit more about some concepts that we're working on there. Of course, a platform is great, but it needs to be operationally excellent. So we need to optimize our teams, need to have our logistics and our PMO, project management workflows going. And that all contributes to that success of the overall platform. And of course, there's our core network, continually enhanced, continually developed, and as new features come online, integrated into the platform itself. That key staff component, we have some new faces that are very important that hopefully will be making the rounds to this larger community that I'm speaking to this morning. James Deaton is coming in to our organization as our new Vice President for Network Services. He's starting in March. Many of you worked or knew Rob Vitsky, who was the previous Vice President. So James is stepping into those shoes. That was after a 6-month search. And he will be managing all of our portfolios domestically and internationally. So that's a big change for the organization. We're quite excited that James is coming in. He has a strong background in research engagement and software automation. Also, again, referencing folks that were with us in the past, many of you worked with Dale Finkelson. You know, very great coordinator for both our domestic and international use. Thomas Araneta is taking that position. He started in January. And again, he comes with a deep technical and community experience in the domestic US, and he'll be making the rounds coming up as we go forward as well. So I wanted to make sure both of these faces showed up in our presentation because they're very key members of our larger team. We're also building our domestic team. We've been shifting our engineering from contract staff into Internet 2. We had a long-standing collaboration with Global NOC to provide our engineering services as well as our NOC services. Global NOC's continuing in that role, but now we're bringing the majority of our engineering services in-house. So you may see a shift for those of you who interact with our staff over time. We're also adding staff to project management, security, contracts, and grants. So can't really stress, staffing is important for us, and we're wanting to increase our overall collaboration, reduce time to delivery of new services, and increase our overall success there. I'm going to just kind of touch on our domestic things. Our backbone is performing well. This is our next generation infrastructure backbone. It consists of 94 400 gig links and a handful of 100 gig links. There's effectively 27,000 terabits deployed capacity, terabits per second nationwide. There's 1.6 terabits per second coast to coast. And all cities, all DMARCs have 800 gigabits per second, up to 1.4 terabits per second exit capacity. So a lot of capacity transiting the United States. It's a disaggregated system. These are not monolithic core routers anymore. They are disaggregated devices, meaning that there are 2 small devices, 1U in even most major cities. Some major cities have 4 if they're cloud peering cities. For example, in this case, Chicago. Now Chicago has 3 different sites, so there's even more. But in the case of a single site, there can be up to 4 routers performing a service. In this case, there are path equivalency for all of our cloud connections in Amazon, Google. And so this is a key architectural change for us that's been going quite well thus far. It's all based on SR MPLS. Very simple, no controller, shortest path calculations, and it allows for a lot of different high capacity between cities throughout the US. We're also building our new API layer, as I mentioned. This includes everything from business integration down through federated identity and access management, down through logging analysis and reporting. Again, I'm just touching lightly on this since I only have a little bit of time. It all wraps into a common console. Unfortunately, this is not an international service example. This is a layer 2 example. In this case, between one of our regional networks and Microsoft. And here you can see that there is a full provisioning view of the service as it stands, complete with data representations of the data rates that are traversing this particular service. So our goal is that all of our services will be front-ended by this console, whether they're domestic or international. So in the case of an international transit VLAN, one could authenticate into this console, pull up the VLAN, and see what the activity is and the endpoints are. Shifting a little bit more towards international, we have a bunch of different areas of effort here. We're bringing our first global exchange points to 400 gigs. We're bringing up our first transoceanic 400 gig links in a partnership with ESNet. We're supporting additional development of transatlantic links in other parts of the world. Our first link is in the Atlantic. We're obviously hoping to facilitate link development elsewhere. We're starting a new domestic consortium. It's an expanding and existing domestic consortium. I'm sorry I misspoke, called APREX. And I had mentioned our data caching services as well. And I'm going to dive a little bit more deeply into this. So our global exchange points in Washington, D.C. and New York, and a future exchange point in Boston are all going to be brought up to 400 gig. Currently, they're running on Juniper QFX switches. We'll be transitioning those over to Arista PR3K switches to have all 4 capable of 400 gigs. This is in step with both our backbone and also the new link capacities that are coming online. We'll be using EVPN for the majority of those circuit provisionings, and we're going to cross-integrate all of that through NSO and the console, the Insight console that I mentioned previously, to provide health and monitoring. So this is really intended to be a uplift of all our exchange points and a reintegration of those exchange points into our core. And we'll see why that's important coming up. This makes sure that those exchange points are integral to our software platform. It's intended to be a system, and then that way we can layer in additional NSI and sense functionalities into those platforms as we go. Mention the 400 gig transoceanic links in tandem with Canary and ESNet. There'll be 3 by 400 across the Atlantic. Coming online in the middle of 23. So that's part of the reason that we're driving those exchange points to be 400 gig capable. We think that these are the first links of many that will be coming online at the Atlantic. There's already various efforts underway to bring on additional links either into New York, Washington, or Virginia Beach to provide backup capacity for this. And also not shown here is work on the Arctic, which hopefully will be covered in some other presentations. Mentioned the goal of looking at 400 in other parts of the world. We're starting to have some conversations with our various other consortiums, APONet, the folks in South America, and then supporting Norgenet and the other European efforts to, on Arctic Connect to bring 400 gig up in those areas. Now, our role would largely be logistical and contractual, but we have a fair amount of experience now. So anything we can do to facilitate those developments over time is key. And we see all of these markets as being, good potential in the next 12 to 36 months. Swinging back to our domestic consortium, I think we've spoken in the past about APREX, which was an effort to coordinate between Internet 2 and PacWave. Again, I have limited time, so I'm not going to dive too deep on this, but we're in the process of bringing the consortium members back together and expanding them to create a larger domestic consortium of link and exchange point operators in the United States. We're going to, for now, it's called APREX 2.0. We may rename it coming down the road, but the goal is to improve the coordination of activities, of the international exchange points in the United States. Right now, they're all operated differently and are often working together, but not in a coordinated fashion always. So our goal is to change that. Really to also enable sort of funding vehicles and grant opportunities to be fully optimized, and also to make sure resources are being used efficiently and features are consistent across. So this was an idea that formed several years ago, and now we're bringing more partners in to try to expand it and really start moving forward. So right now, our vision is that we would have 6 partners inside the North American footprint, including Canary, who operates Moxie, and Starlight, the Starlight Exchange, Ampath out of Florida, IU, who Hans will talk here in a few minutes, and PackWave, and of course the Internet 2 exchange points. And each of these entities brings strengths to the table. Internet 2, for example, is fairly strong on transport and software development. Other folks are strong in funding and other research programs. Of course, everyone has unique experience throughout the world. So trying to bring a cohesive consortium together to facilitate all the things that were in my first slide that we've been hearing to achieve all of the various goals is key in kind of doing better coordination. So that's the vision, is bringing these parties together. From a network perspective, it might look something like this. We have links in from the West Coast, links in from South America, links in from Europe and Africa, and they all come together into the exchange points into this conceptual fabric. It also gives us an opportunity to build both dedicated wave systems and also leverage the Internet 2 core or the regional core networks inside the United States for conveying the more routine traffic. So, there could be in some ways some bifurcation of use depending on what application is being served. So again, these are some concepts about how these networks can be knitted together, either using the Internet 2 common core or dedicated links between the various exchange points. And all of these links shown actually are sort of conceptualized to be 400 gigs. So, in some cases, you've got potential applications for data mover, and in some cases, you've got applications for more routine traffic. The excitement and the fruition, though, of some of these technologies that are coming out are to start using things like SRTE and FlexAlgo to start to knit all of these things together so that you're not bringing redundant resources, and all of your resources, whether they are a dedicated link or a common core infrastructure or different exchange points, you start to be able to knit all of them together using some of the new developing technologies. So I just wanted to throw one slide in here at the end about how these things can start to come together using things like SRTE. So one concept for the Internet 2 core is that we bring SRTE online, the feature that's coming up on the platform. We bring something like FlexAlgo forward. BGP-CT, which is a developing concept, isn't there yet, but maybe it's next. And so, you begin to form even controllerless applications where in a normal traffic situation, which is what I've shown here, we have our disaggregated core, we have our FlexAlgo style controllerless network where you have the whole core participating in sort of your best effort traffic, but you start to differentiate different SIDs and different applications for each of the algos. So they've called these algos, but maybe you have one for transit traffic heading south and one for transit traffic heading north and another for a dedicated link. And you use some fairly simple technologies to label traffic coming in to determine which link it traverses and traverses through, for example, a core like Internet 2's to go to the adjacent exchange. So, kind of the promise of all of this is that we begin to start to see a merger or a lack of differentiation that's needed between the core networks and the exchanges that are participating in a given set of platforms. So anyway, just a kind of pie in the sky concept to throw out there. So what's next as far as the Internet 2 platform goes? We've got to complete our development of the 400 gig that we have in the pipeline. That's sort of quarter 3 of this year. We've got to deliver our software features, which includes Insight Console and the underlying APIs. That will come fully online for both the domestic and the international platform targeted at the end of the year. We're going to experiment with some of these use cases that I showed you in the previous slide throughout this year to support some of these sort of data intensive use cases and then some of the more extended operational transit use cases, looking at that in 23 and 24. Meanwhile, we're going to work on this consortium side because it's not just about the technology, it's also about bringing everyone together to have common goals and shape our roadmaps, both in Internet 2 and our larger consortiums. So look at doing MOUs and roadmap work through 23 and do some initial technology development for the platform there, and then expand the footprint, expand the consortium, and add features into 24. And then hopefully past 24, we begin to merge our sort of operational paradigms, our core technologies, and the software stacks into a more cohesive system, at least within the US over time. So that comes, down towards 24. And that's about it. I know that was a lot, but I'd be happy to either take questions later or whatever we have time for.
Thanks, Chris. That was amazing, and to see how things have evolved over the years. Within a short time of COVID, a lot of things have been deployed and new technologies have been added on. And I can see the trend that you're pulling back the technical staff rather than outsourcing contractually. You're pulling back the staff back into Internet 2. That's amazing. Any question from Chris? If not, I'll ask you to send your slides over through an email. I'll send an email to you so that you can quickly upload the slide to us and we can share with the community here itself. I'll next ask Chin Gyok. Where is he? Oh, there he is. Thank you, Chris.
All right. So hi, my name is Chin Guok. I'm the CTO of Net. Obviously, Chris's talk was so awesome that he blew out the screen. I'm not going to be able to do the same, but hopefully you'll get something out of this. All right, so I'm going to give you a brief update on the network that we just deployed. This was just about middle to end of last year. I'll give you kind of just a quick rundown on some of the aspects of the network, and then I'll kind of talk about things that we're looking at for the future. So YesNet, basically in a nutshell, we're looking at capabilities of 4x bandwidth, higher capacity, more resiliency. These are all pretty standard things that we typically see in a network, right? So there shouldn't be anything here that is kind of out of the ordinary. But I think one of the areas that we're most proud of is the notion of consulting. And so we're not just a network that provides connectivity, but we do co-design with our end users to allow them to optimize the use of the network. I'll briefly kind of go through the design of YesNet. It's pretty simple, right? It's a hollow core design. Within the core, essentially, we have high capacity, high resilient, really simple forwarding. So we do use SRMPLS. We do SRTE. We're actually deploying a PCE as well, a path computation engine. The services edge is where things get really interesting, right? So this is where you actually deploy your services, right? Your L2 VPN, L3 VPN. A lot of your QoS marking, filtering, security services are all on the edge. That's not me. All right. All right, we'll just keep going, right? Do you guys want to take care of the Zoom session real quick? Okay, so I'll just keep going just in the interest of time. So this is our this is the capacity map that we have. Primarily, a lot of the waves that we're putting up 400 gigs. We have some waves that we can go up to 600 gigs depending on span. So 15,000 miles of dark fiber, right? We have 300 lease spaces. A lot of this is essentially the amplifier huts for the for our OLS. We have about 14.6 terabits of aggregated capacity that we've deployed so far. And currently, it's like I said, it's primarily 400 gigs services. So to our end sites, there are a bunch of them that are starting to go to 400 gigi. Along with just the basic infrastructure, we have our whole services and capability structure, right? And what we did was we kind of went through and we had to determine exactly what kind of services do we need to run in the actual network at different layers in order to support the end services. So everything that you see is green is what the user actually touches. Everything else are supporting services that are needed to essentially provide those services. One of the big focuses that we had with ESNet 6 is really on this idea of automation and orchestration. So up till now, we've had some automation and stuff like that, but a lot of it was actually designed by network engineers like me, and we are terrible at actually following best practices for coding. And so when we came to ESNet 6, we basically decided we need to kind of go back and restructure and re-architect the entire software stack, right? So we got a software architect to come in, we looked through all the code that we wrote, we went in and restructured it. This is kind of a really simple view of what it looks like. But now we have very cleanly identified and delineated APIs. We have very well-defined functions. And you don't see this, but just to give you an example, right? So when I started about 25 years ago in ESNet, there was about maybe 19 software engineers, and we wrote code as well. Today we have, it's 19 network engineers, right? So today we have about 30 network engineers, but we have about 29 software developers. And so there's this skew towards actually creating and building software expertise, because as we move forward, a lot of the advantages and gains that you see is not on hardware or network engineering. It's really building the software that is customized to the services that you want. This is just a quick idea of the areas that we're looking at in terms of the software development, right? So there's assurance, provisioning, security, analytics, and then a unified data model. What happens is on the provisioning side, that was probably the main focus for ESNet 6. All the other stuff were actually being done within the ESNet 6 project itself. We formalized the provisioning aspect of it, and this is the architecture. So you'll notice that there's this notion of an orchestrator. We actually use Cisco NSO to do the provisioning and the abstraction for our devices, and then along with that we have like the source of truth, which is our ESDB and things like that. So that kind of gives you a general idea of what our software, the software stack looks like. All right. The last aspect that I wanted to bring up to you would be on the top right, and that's the high-touch precision platform. So that's a completely new platform that we introduced into our network as part of ESNet 6. So the idea of the high-touch platform is that it provides a lot of flexibility, but you can actually do things at line rate. So what it is essentially a couple servers with FPGA cards, and it's deployed at every location that we have a router. To give you an example of some of the things that we can do with it, we basically use the FPGA to parse packets that come in. So we mirror the packets that actually come into a network, we feed it up into the FPGA, it actually will do flow aggregation for us, right? And this is just one example. So right now, the FPGA is not in the forwarding path because it's a new platform and we're being conservative about what we do. But there is ideas about putting the FPGA into the actual forwarding path. So you can do things like NDN without actually having to update the your router OSs, right? So here's an example of the high-touch data that we pull out, we put it into our back-end analysis system that we already have, right? And so you'll notice the blue area, which is the IP fix, that's sampled at 1 in 1,000. You'll notice that there's this kind of, you know, gentle shape. But if you would actually look at unsampled traffic, you'll notice that the traffic profile is significantly different. So what it does with the high-touch stuff that we're looking at, and we can look at every packet that comes into our network, and we can do this in real time, right? So what it actually does is it actually gives us a lot of capability in terms of understanding how the traffic pattern actually looks like. In addition, the bottom right, you'll notice this thing called the packet distribution histogram. So just for grins, we said, why don't we put some functionality into the FPGA card and see what it can do? So again, this is actually done in real time by the FPGA card. It looks at the packet distribution, it's unsampled information, so you know exactly what the packet distribution looks like. One of the things that we've done is to make the code in the FPGA usable. So if you are familiar with P4, right, a lot of the processing is actually done using P4. All the externs that are interesting stuff like the histograms and all that, that's actually developed by us using Verilog and compiled into the FPGA card itself. Right. One of the things that we're exploring today is to not only just explore the, export the flows into our current reporting systems, but we're actually building a database. And the idea here is that you can actually query, anybody can query the database, well, not anybody. Anybody in ESNet can query the database using simple SQL. So if you understand SQL, you can actually query the database and find information that you want, right? We're using ClickHouse as the database. We currently have about 2.5 billion flows. This is out of 11 high-touch nodes. So this is a partial deployment, right? We're looking at closer to like 90 high-touch nodes. And so our goal is to basically retain about 30 days of flow query in fine detail, right? And that kind of comes up on a back of an envelope calculation to about 1.15 trillion rows at about 100 terabytes. This is an example of a query, right? So essentially here we said, hey, do a packet size, not packet size, a volume query basically on all TCP flows for essentially 12 hours in our network, right? And so it's a really simple query. You kind of get the distributions there, but if you look at this, it's kind of an eye chart and you can't see it. So we processed about 2.4 billion flows and it took just under 10 seconds. So the really nice thing with ClickHouse is that you're able to run these really intense, queries on these huge data sets and kind of get your answers back in reasonable time, right? And our security folks are kind of going crazy over this, right? Because now you can look at every packet that comes in. You can basically start looking at are packets coming in from a certain nation state? Are you looking at just, how many flows came in with just SYN packets and no SYNACs or FINs? And all that can be actually done through a simple SQL query. With the SQL query, what you can actually do is you can actually start running visualizations. Oops, here we go. So here are some of the visualizations that we did just for fun, right? So you can do things like host fingerprinting, where you can do anomaly detection, background radiation, right? Log analysis, port scans, yada, yada, yada. One of the things that we are interested in doing is to really leverage AI and ML, right, with this information to enforce policies or specific action. And so that is why in ESNet 6, I kind of mentioned before, right, one of our main focuses was automation and orchestration. So we have a basis for us to enact any policy or any action that we want in the network. Right now, a lot of the decisions is made by an engineer. With the high-touch stuff, this gives us the information to make those decisions, right? And now if you throw AI ML in, now you're able to actually have a dynamic network, a set of dynamic network configurations, right? Because you actually do have the automation orchestration, and then the high touch allows you to have a feedback loop to understand whether you are causing problems or whether, the expectations of what you did was correct. All right. So that was kind of ESNet 6. I've got a bit of time. All right. I'm going to talk about what we're looking at with ESNet 7. So we just finished ESNet 6. We're starting to explore what ESNet 7 will look like this year. And so this will just give you a rough guide on some of the things that are guiding the decisions that we make as we go into the next generation of ESNet. One of the largest drivers is this notion of the DOE ASCA IRI. If you're not familiar with DOE ASCA, that's the program office that manages the ESNet network. IRI stands for Integrated Research Infrastructure, right? So one of the things that we find, especially when we talk to our end users and our scientists, right, and you say, you have this thing that you're doing, right? So you're doing fusion research, or you're doing light sources, or your accelerators. What is it that you need? And almost all the time they tell us, I need this kind of compute, and I need this much storage, and I need to have it, the data lasts for so long, right? In almost no cases they will ever say, oh, I need this much networking, because to them networking is just an afterthought, right? So the idea of the IRI is to kind of elevate networking to what we call a first-class resource, similarly to how you would think of as compute and storage. So let me give you an example. If you had a job that you needed to run, right, and you basically talk to a scientist, and they'll say, okay, I need you to dedicate, 1 million cores. I need you to give me, 100 petabytes worth of storage so that I have the data that I store. But they never talk about networking, right? But the fact is, a lot of what we see is that networking is actually integral to the workflow, because the work that they do, the instruments and the compute and storage resources are actually not located in the same place. And so if you have those requirements, what if you could actually tell the network and you say, oh, by the way, I'm going to need 400 gigs, right, 400 gigabits per second of networking for the next 10 hours because I have a compute resource that I've already reserved, and I can't have the network go down, and I can't have you giving me like 10 megabits per second because I need to move a huge amount of data, right? You never hear these kind of things, but what we're seeing is that as we start talking to the scientists and we're making them more aware about networking, right, we're starting to see these requirements. And so the idea is, again, to elevate networking as a first-class resource like you would compute and storage. To that end, there was this white paper that was written that essentially brought the idea of integrated research infrastructure, which is connecting the instruments, networking, compute, storage, and treating it as if it's a single virtual facility, right? As opposed to today where we have separate administrative domains, separate security policies, separate APIs, separate provisioning. One of the things that was a follow-up to that initial white paper, which happened in calendar year 2022, was the notion of the ABA, which is the Architecture Blueprint Activity. So we took the white paper and we basically said, if we want to take this one step further, what does the architecture actually look like? What are the requirements, right? And so what happened was the activity actually broke down into two areas. It talks about the pattern blueprint. So these are the requirements of the workflows, time sensitivity, data integration intensive, long-term campaigns. And then the practice areas are the ways that you will implement it. I'm not going to read this, but this is kind of generally the idea and the definitions of each of the pattern blueprints. So it's time sensitivity, time critical sensitive requirements, right? You're motivated by things like timely decision making, experiment steering, virtual proximity. So if you do like a digital twin and you need feedback to essentially guide the experiment, you don't want that feedback to have latency that is so high that it doesn't make a difference by the time you actually start adjusting the parameters for your experiment. Loss of data fidelity. The idea here again is if I'm generating 400 gigabits of data per second and you're only giving me 100 gigabits of networking, you're going to lose a whole bunch of data that I cannot recover, right? Data integration intensive. The idea here is that we're starting to see multidisciplinary analysis of data across different disciplines. And so you need to start pulling in data from a whole bunch of different places. In addition to that, there's this whole issue of tracking metadata, provenance, reproducibility. And long-term campaigns, really, the idea is that, you have these experiments that run decades long, right? And in those decades, the problem you have is that you're going to be upgrading stuff. You upgrade your network, you upgrade your compute. So how do you actually make it so that it's congruent for the actual experiment, so that all of a sudden, they don't have to rewrite the whole software stack, or they don't have to change the way that their workflows actually are done because you've changed certain hardware and now, the capability is not there. Practice areas, I think, this is very quickly, just, resource cooperation, cybersecurity and federated access. User experience is extremely important. Most of our users are not experts in technology, they're experts in science, and that's what they want to do. So, this is where we have to bridge the gap. Workflows, interfaces, and automation, scientific data lifecycle, and portable, scalable solutions. Right. So, based on that, one of the things that we did was we said, well, how does it impact us, ESNet, a network, right? You have all these requirements that we're talking about. So there are about a dozen things here that we came up with that are areas that we want to pursue to actually support this. And these are things that potentially will be integral to what our design for ESNet 7 will look like, right? So we want to have a predictable networking, high bandwidth and rich connectivity. I think that's kind of a given. Support application network interaction, where the whole idea was, now your network can actually your application can talk to the network to understand what's going on. It can negotiate for resources. Again, it's the same way that you would work with like a compute resource, right? When something's running, you can say, what's the utilization of my job? When is it going to finish? Am I seeing a core dump? Is there an error that's going on? Today, you don't see that for networking, but the idea is to build that into the networking so that the application can make better decisions, right? Friction-free data movement. These are things like the Science DMZ, right? Integrating Globus, our DTNs. Network computational storage capabilities. So one of the things that we're doing is we're starting to deploy caching the network. We're also starting to explore edge compute, right? So it's not just centralized compute like a high performance center or a cluster, but you have these smaller edge compute functions that allow you to basically run specific functions that are tied to the instrument. Again, multimodal network connectivity. We're looking at wireless sensors. Supported programming constructs. I think one of the really important things is that if you do actually have a network application interface, it has to be standard, hopefully, because you have a lot of networks that you deal with, and that's something that has to be socialized across the network community, right? Common access frameworks, resource allocation policies. That's kind of an interesting thing because we have 3 supercomputing centers within the DOE complex. Each of them have different allocation policies. So you can't just take your job from one supercomputing center to another because you may not have an allocation quota on that system. Development and testing environments, co-design services, and then engagement and partnerships. So with that, I am done. All right.
Thanks, Chin-Gyo. That's very on time, very interesting. And if I look at it, it's very similar to also what the Internet 2 are doing as well to standardize and automate on the back end. Next, I would like to invite Hans from Indiana University, who is a co-PI of Transpac, to give an update on the international network.
Thanks, Francis. And you're one of the co-PIs of Transpac as well. So hi, I'm Hans Adelman. I am the network architect here at the International Networks at Indiana University. So I'm going to talk about what's been going on the last few months with us since we last talked in August. So at the last quarter of last year, we had a bit of a leadership change. Dr. Shupp left to go to TAC, the Texas Advanced Computing Center, and Jim Williams, who many of you may know from his previous work in Transpac, has stepped up as our temporary director to lead the team during this transition. Our team is still strong. I'm here as the network architect. We've got Brenna Mead as our network engineer, Ed Moynihan as the co-PI of NEAR as well, and also our engagement specialist, and we have a project manager, Heather Hubbard. So real quick, Transpac is an NSF-funded project. Right now, we fund two different circuits, one in partnership with Pacific Wave between Seattle, Tokyo, and we are part of the Guam-Singapore Circuit Consortium, which has been running since January 2020, which, of course, links Cineran to Gorex, and includes RNet, Internet 2, us, Arena Pack, Pacific Wave, University of Hawaii, and Cineran all contribute. Looking to the future, we just got back from a very busy PTC, and we're looking towards 400 gig in both transatlantic and trans-Pacific. We're looking to step up our support for international science collaborations and experiments with SC Asia, the upcoming Data Mover Challenge, SC23, which I'll talk about in a little bit. We are really trying to, as Chris and Chin both said, work directly with the scientists and science engagement to bring the network, to the instrument and help them move their data as efficiently as possible. TransPac is a partner with the FAB project, and we're helping work with that network testbed, connect them to the University of Tokyo, working with some of our friends at NICT to make that happen. And of course, we're continuing to support LHC1, and we do a bit of work with them, starting to get back into the network research side of things as well. So I did want to call out APONET or APONET, whichever you prefer. This is our latest map. This is a really great collaboration of people, and I think Chris already touched on this a little bit. So I just wanted to first announce here that Steve Maddox is now the new APONET coordinator. He is from RNet. I believe he may be in the audience. Anyways, I must apologize to the group that we haven't had a meeting in a while, engineering or leadership. We will get back to those. I just need to get out some doodle polls and try to find some good times for someone. Anyways, we have a few activities. We're trying to support highly available connectivity, get those backup paths in place. As we heard during the routing working group discussion there yesterday, there was a bit of discussion about how many cables are being cut here and there, and that in a lot of cases, maybe having two paths between two places is not enough now. So the APONET provides a wide range of backup paths for everyone. Cooperation and coordination. Again, our engineering meetings have kind of fallen off the calendar. I will get those back on as soon as possible. We're exploring that network research, looking at experimentation with high bandwidth demand applications, and continuing to troubleshoot end-to-end connectivity in concert with the routing working group. And of course, doing experimental support for SC and other conferences like that as needed. And of course, if you haven't seen the APONET NetSage dashboard, that is worth checking out. You can see a live look at what kind of traffic is transiting. Yeah. Real quick, the other things we do, since I mentioned it before, we have another grant that is on the Atlantic side of things called NEAR. It is an NSF program as well. We have 200 gig connections between New York and London and New York and Amsterdam. We are part of the ANA collaboration, and just this last December at the Internet 2 meeting, the ANA signed its next MOU. We have a series of partner circuits, and we all contribute measurement data to the ANA NetSage instance. And we do work, on the LHC support. We are looking at astronomy with EHT and genomics as well. And of course, NEAR also will support network experimentation. And I hope to see more of that this year across the Atlantic for SC. And real quick, there's the partners for the ANA. And there's a diagram of what the ANA looks like. We're working on a better map now, but this is just a screenshot from NetSage. So TransPac, I wanted to call this out. TransPac and the APONET especially, we worked really hard and were able to well, I'll go to the next screen. These are some of the network research experiments that we actually used APONET to move data between places in the Asia Pacific region all the way to Dallas in Texas for SC22. We actually had 600 gigabits per second to support 6 different demonstrations from NICT. And these are the 6 paths we used. It's pretty much all of APONET, but there was enough room with this great collaboration to also have production traffic not be affected during these nearly 600 gigabits of demos flowing across APONET. And I think that was pretty incredible work by everyone in APONET. So SC23 is coming up in Denver. It turns out that I'm the SciNet chair this year. So one of my big pushes to the SciNet team this year is to focus on more demonstrations from the international community, both Transpac and here. I would really like us to go higher than 600 gigs if we can across the Trans-Pacific connections. Brenna Mead, who I know you all know from the routing working group and Transpac as well. She is the co-chair of the network research exhibition this year, and so she will be reaching out to help coordinate that traffic. And then, of course, we're going to bring back the SciNet Theater on the show floor, which will allow this year researchers who do not have the resources for their own booth to continue to showcase their experiments. So if you have an experiment you'd like to do, if you have some research you'd like to show off, but you don't have the money for a show floor booth, please talk to us. We can provide a place for you to do those experiments and talk about them. And then, of course, the preliminary submissions are due in June. And if you have any questions, there's the email address. So real quick, we're all talking about silent engagement. I just wanted to put this out here. Like I said, improved collaborations with international partners. The Data Mover Challenge this year, SC23, TNC. TNC is coming up in a few months as well. And then, of course, understanding who's using our network, using NetSage or any of these new high touch or real-time telemetry things that are coming out. Hopefully we can deploy those to better understand who's using our network. And, again, I would call out the routing working group and the work they're doing to some of the routing and data transfers. And look at that right there. So real quick, if you didn't see Brenna's talk last night or yesterday morning, I guess, for you guys, the routing working group is growing. There are 170 members, over 20 countries and 80 institutions. They've had 18 cases to date, 15 of them solved. This group is really growing and really doing great things. And of course, if you'd like to join that routing group, you can email any of us there, Brenna, myself, or Warwick, and get on that mailing list. We also have the APAN Slack instance and the routing channel. You can join. There's a lot. I wouldn't say it's used, but there have been some really interesting cases come in through Slack, so that's fun to watch there as well. And of course, I'll just say, Chris talked about APREX, and we are really excited to be part of that. So I will skip those slides because he already talked about them. And then real quick, I just wanted to kind of show NetSage. And I did talk about the APONET NetSage, and this is that dashboard. So here you can see what traffic is doing across APONET. And you can actually even dive into that a little bit more and look at some of the anonymized flow data and see what destinations, what flow players are actually happening at any given time. Or this just shows the last 7 days from when we took these screenshots. I'm not brave enough to do a live demonstration, but this is just kind of an example of some of the things you can get out of NetSage. And then, of course, I'll pick on Francis some more and just show top flows received by SingerN as well. And then, of course, you can dive into the individual flows as well. So anyways, just a quick shout out. If you do know of any U.S. science collaboration sending big data, Trans-Pacific, Transatlantic, that have engineering issues, let us know. We're happy to help. And that's it. Thank you.
Thanks, Hunt, for the presentation. I do have a question for you, and that is, you said that you're providing a booth for people to put up posters or presentation at SC23. Am I correct to say that?
Well, sort of. In the past, we've had what's called the Signet Theater, and that theater gives people an opportunity to talk about the research they're doing. This year, I'm expanding that slightly, where we won't provide not everyone's going to get their own booth, but we will provide a space for people to come and talk about the research they're doing if they'd like.
Okay.
And put up digital posters as well.
Okay, my understanding is that you can put up a schedule of talks at that booth, and people from different regions, like from Nepal, can share their research projects through the booth. Am I correct to say that?
Oh, for sure, yes.
Okay.
Share that. Let me share the slide again so you can see the NRE.
Okay. The other thing is, I'll encourage those of you who are online or present, and if you want to share some of your challenges with your network of thinking, you got 100 over network specialists out there to assist you, and that's what the working group is, and it has managed to solve a lot of the problems, of some of the problems that we have encountered, and I think that's a good way of doing things. Thanks, Hunt.
Thank you very much.
The last speaker is Akashi-san, and he will talk about Signet 6 and beyond. Akashi-san?
Yes.
Okay, the floor is yours. Yeah.
Let me share the file. Can you see it?
Yes.
Thank you for introduction. I'm Osama Akashi of NII. Sorry for remote attendance, but I'm happy to have a presentation at the APAN. So I would like to talk about the Signet update, but especially focusing on the operational aspect of Signet 6. This is a brief introduction of Signet. Signet is a Japanese ultra-high-speed academic network and connect Japanese academic organization and large experimental facilities, supercomputers, and research data platforms. And Signet provides connectivity to those organizations and provide such a service. Actually, yes, new Signet 6 started in April 2022. In Signet 6, we applied the 400 gig nationwide and increased Signet node and strengthened the global connectivities. So, what changed? Oh, sorry. Oh. This was a Japanese domestic topology of 400 gig lines. So red line shows the 400 gig line topologies. We connected almost 47 prefectures in Japan by 400 gig technologies. Due to the technological restrictions, Okinawa, mainly Naha, are connected using the 100 gig lines. And this tab shows the number of organizations connected to Signet. We connect almost national university to Signet, and the total member organization of Signet is 1,006. It's information of the January 2023. So this shows the detailed access line status. This tab shows the number of access line divided by the bandwidth. Member of organization, member of the SciNet organizations are connected to the access line using the 400 gig or 100 gig or 40 gigabps and so on. And this shows the access line number of access lines. SciNet 5, namely 2022 April, is shown this lower lines, and the red number shows the SciNet 6 access line number of access lines. So as you can see, we can observe the four increase in 400 Gbps and 72 increase in 10 Gbps. So we can observe the increase of the bandwidth as far as the access lines. And this shows the international map of our networks. In SciNet 6, we added the new line between Tokyo and Guam and keep the conventional line between Tokyo and Singapore and Tokyo and Amsterdam. And we increase the bandwidth between Tokyo and Los Angeles and New York. As far as the new EU line, it will be in operation from the 2024. It's under procurement, but the line route from the 2024 is not yet determined. So we are now preparing the procurement of the new Japan EU lines. And the previous APAN meetings, I reported that the router installation in Singapore was finished, but in September 2022, remaining one router installation in Guam was finished and became in operations. So we finished the all installation of the routers in the world. So this shows the international lines and collaborations. And in the previous meeting, I reported the ANA signing was not yet finished, but after APAN54, we signed the ANA collaborations for Atlantic areas. So we are now collaborating with APONET, AER, and ANA. So this is a sometimes complicated graph. So this shows our implementation schedules. So upper layer shows the original plan, and the lower part shows the actual actions. As you can see, construction of optical transmission layer is was implemented as on schedule, but the construction of the packet transmission layer was delayed about 1 month, as shown in green lines. And furthermore, installation of router and server was heavily delayed due to the router delivery delays, as shown in blue lines. And it means that the connection verification and comprehensive verification is also delayed, as shown in the orange lines. So final deadline for migration was delayed. So we have to do the shortened this migration in shortened migration periods. So this shows a detailed migration schedule. The number of access lines to be migrated is more than 1,000, and we have to migrate these services, avoiding the service suspension time less than 30 minutes. And as a consequence, we have to do this work on weekend almost. So migration on weekend is more than 800, and migration on weekdays are more about 300. This shows the implementation of the SciNet node. We constructed more than 7 70 SINET node. Sorry, it's not SINET node. So in this x-axis shows the timelines and y-axis shows the number of SINET nodes. So we start the verification of connection among IP routers and lines. Was the end of the 2021 December. So we have to start 6 data centers for equipmentations. So end of the January, we only have the 18 SINET node. And in the February, we do works for installation. And end of the February, we equip the 70 SINET nodes. So as you can see, we have the overlapping term of the migration and verifications. So, and we have some large expenditures event. So we are doing the very tight schedule. And but after gradual equipment, we finish the or installation of SINET node. Oh, this is a projection only slide. So actually, a certain number of problems occurred even after SINET 6 started operation, namely after April. So you can see the several number of failures are observed. So this many failures occurred namely in 400 gig line cards. And the majority of this 400 gig line card failure were line card restart. So we were suffering such heavy failures. So we have to do the maintenance actions during this installation period. So end of the 2021, we decided to fix operational routers OS, but after that, we have to update of the router OS. And we unfortunately, we observed the VPN-related problems at the February and March, and 400 gig line card problems. So we have to update almost all routers OS and VPN problem fixings. So after that, we also observe the 400 gig line card restart problem. So we have to do the patch of the gateway routers and update of all routers operating systems. So we expected the fixings of the line card problems, but after that, we also, we observed the 400 gig line restart problems. So we have to do the patch of the routers again. So we are currently fighting these problems. So I hope these problems have been fixed. But actually, we have other problems currently. This is a lesson learned about the installations. You may think that it is a very in general term, and it is not need to say, but we recognize the importance of this point. Please let me explain about this point. First one is test in the verification environment cannot guarantee complete validity in the operation network. Of course, the network structure of both environment is not the same, and in many cases, test environments are insufficient and limited. So the second point is a little technical. So difference in upper layer configuration might affect the lower layer behaviors. So it is somewhat complex causalities, but it could step on bugs. So it is sometimes serious problems. Third point is hardware problems, and hardware level instability is avoidable, especially when using the latest technology such as the 400 gig technologies. It is avoidable, but have to tackle these problems. So after that, we reorganize important point. First one is sufficient test in time and cases both on the test environment and actual operation network is important. Second point is flexible and sufficient schedule for migration and test on the operation network is also important. And the third point is effective monitoring and observation environment for debugging and verification is also important. So it means monitors and testers in conjunction with the visualization tool at FAIR3 are also essentials. So it is it sounds somewhat a general point, but we reorganize the importance of that point, these points. Okay, that's all. Thank you for attention. Any questions?
Thank you, Akashi-san. It looks as if SciNet 6 have really gone on the 400 gigabit backbone complete almost. And you're taking a lead on this. And Chin Gyok has a question for you. Yeah.
Sorry, Juan, voice is not.
The question is, would you share the vendor of your 400 gig?
Yeah. Actually, we we have a discussion about the router vendor, namely J. But it is a tough discussion and needs the time to patch the OS.
Okay, Sato-san would like to answer that.
Yeah, Akashi-san, I will talk to him later. Is that right?
Sorry, voice is not so clear.
No.
Okay. Sato-san, could you say once again?
Sato-san, you want to? Is it okay to share? That is, I think it's not okay. I think we will share offline.
Yes.
Friend, okay. The other thing is, I can see that you look at all the internet to ESNet and SciNet. They have really gone on to 400 gig, and I'm still on 100 gig and 10 gigs. Things have advanced quite a lot, and I guess there's always issue when you deploy new things, leading edge things, and always a challenge to do that. Yeah. Any question for Paul? Yes. Do you have the mic? There's one there.
Hello, Frédéric Louis from France, Europe. We just received yesterday our 2 switches, which is the P4 switch able to run 32 ports at 400 gig. We are closely working with Sato-san, and we'll deploy soon maybe new switches there. But if you are really interested, we can conduct also 400 gig test with at the packet layer using P4.
Okay, thank you. I got a question for Chin Gyok. Which vendor, now turn it around, which vendor do you deploy, and was there any issues in your deployment of 400 gig?
Yep.
Yeah, so we deployed Nokia routers. We didn't have any issues with the 400 gig routers. There was some testing we had to do with the optics, but the cards were fine.
Okay, thanks. Yeah, there's a question over there. Please, and then before.
Sure. So good morning. This is Ariful Islam from Bangladesh Research and Education Network, BDN. So I have a question from my curiosity. You have established a 400 gig network over the oceans under the sea. So I have the question that what is the do you have any utilization graph? Then you can show it actually how amount the link is utilized. And another question is whether it is using existing submarine cable or it is deploy a separate cable from this project.
Okay, I think the question is directed more toward Chris Wilkinson or Jin Gyok, who this is concerning the 400 gig between Europe and USA. Or Jin Gyok, either one of you? Chris?
It's a new cable build, so it's not so much optimized, but it is with 400 gig intended. So it is a new cable build that's being developed.
Okay. So it's a new cable. Yeah.
Correct.
Thanks, Chris. Any other questions?
I did want to just mention that you know, we also had issues with our 400 gig, although in our case it wasn't line cards, it was the optics themselves that we experienced some issues with, and only at scale. So in our lab testing in small quantities, we didn't see issues with the optics that we used. But when we had several hundred of them deployed in the field, we saw issues with the ASIC timing happening, particularly on the optics between our devices. So I definitely understand what the SINET 6 team went through, and you know, good work on that.
Thanks, Chris. Thanks for sharing on that. And what's the equipment that you have deployed for your 400 gig, the vendor?
So the you know, our primary core network is Cisco 8000 series, 8201s and 8202s, and the optics involved were a third party, 8-lane AOC. I actually gave a talk at TNC that may be viewable, where I talked about our issues with ASIC timing between our 8200s and our third party AOCs. We are in the process of replacing those with 4-lane discrete optics instead. That's an ongoing process for us.
Thanks, Chris. Akashi-san, you want to say something?
Yeah, so we had some discussion with router vendors, 400 gig line card, but they also have the first time to deploy such devices. So we need a lot of time to discuss with the engineers. So, and it is also difficult to find the bug status from the observed situation. So it needs time to fix. It is very difficult to fix. Okay.
Thanks, Akashi-san. Now you know some other people who we can exchange notes with and learn from each other. I think that's good. Any other questions from the floor? If not, then thank you, everyone. Thanks our speaker.
Thank you.
And thanks everyone for coming for this session. And after this, we'll continue on network engineering.